Welcome back everyone to my favorite unit, circuits. Okay, so now we can start a really formal understanding of circuits. The central three variables we consider. Those would be resistance, current, and potential difference, or voltage. Okay, so we've been discussing voltage a lot so far. Let's move on to our next one right here, current. Okay, current is represented by a capital I, and current is a flow of charge. Okay, it is how much charge flows through a given point per second. Therefore, you can write that current is the derivative of charge with respect to time. Okay? If there's a high flow of charge, there's a high current, it means that more charge is flowing per second. When we look at the flow of charge or the flow of current at the microscopic level, at the nanoscale, when we exhibit the elementary charge carriers, the electrons that are moving in our conductors, we see that those charge carriers themselves have a certain velocity, okay? And we might be able to express our current I as equal to the number of charge carriers, little n, times their velocity v, times the area of the wire through which they are traveling, cross-sectional area, of course, times the charge they carry. Now, derived from this equation, we have capital J, which is current density. How much current is flowing through this cross-sectional area is what it tells us. So your current density is going to be your number of charge carriers times the charge carrier's velocity times the charge that each individual carrier exhibits. Okay, these two are equations that are not on your reference sheet. They are just derived equations. Okay? The understanding of what these two means is important to understand the next equation that is on your reference sheet, that your current is equal to the integral of your current density multiplied by the area differential. Okay, because your current density is the derivative of current with respect to area. Okay? So if we integrate that with respect to area, then we're going to get the current. And notice here that this is a dot product. So we need to integrate along the length of the area normal vector. Okay? I think we've done a lot of practice with integrating density over distances. So just some little nuances here. So in the case where you're given J, in the case where you're given current density as a function of distance along the wire, then of course you would do your dot product with your area integral, and you would know that you would need to do something to this integral to get it to work, because you have a function of r integrating with respect to a. Okay? So naturally we need to do our change of variables. Let's say we're dealing with a circular wire. So if, for example, your current density as a function of r was dealing with r as the radius in a spherical, or I should not say spherical, cylindrical wire, then that would mean that at different points inside your wire, there is different current density. It's common to have the greatest current density at the center, but that's beside the point. Of course, if we're dealing with a circle, we know that the differential area of a circle must be derived from the area of a circle. Area equals pi r squared. So if we differentiate both sides, the area differential equals 2 pi r dr. Okay? So now that we have the area differential, we can substitute that back into our integral and integrate our current density as a function of r dotted with 2 pi r dr. And now we have our variables that agree, so we can integrate freely. Okay? So in electrostatics, you had the equation that your electric potential, capital V, was equal to your Coulomb's law constant K times your charge Q over R. Here in circuits, this equation is no longer helpful to us, okay? So that equation is no longer how we are going to be calculating voltage or potential, because now we're no longer dealing in electrostatics, we're dealing in electrodynamics, which is another name for electricity, okay? So we are going to want to recall that the voltage V has units of joules per coulomb, okay, where joules is a unit of energy and coulombs is a unit of charge, okay? So the voltage is a unit that tells us how much energy does each coulomb carry as it flows through a circuit, okay? A high voltage means that every coulomb of charge carries a lot of energy. We're going to cover EMF in much more detail when we get into the magnetism unit, but I want you to understand that voltage and EMF are the same thing. The classic example, the classic analogy that is often used to describe circuits is the analogy of water. If I had a dam and I had a high amount of water on this side of the dam and a low amount of water on this side of the dam, this would represent a change in height, okay? And what does this change in height tell us about the dam? It means that if I remove the dam, a lot of water from the left is going to flow very vigorously to the right, okay? Meaning that the water on the left is very much so forced and compelled to move to the side that has less water when it gets the chance to. This difference in height, the difference in water levels, is analogous to a difference in electric potential, okay? Electrons, charge, electricity, always flows from high potential to low potential. And that is the governing body by how electricity moves. Electricity, or rather electrons, because in our study of electricity, electrons are what is carrying charge, electrons are what is transporting charge. So electrons always move from high potential to low potential. If there is no potential difference, meaning if the two water levels are at the same height, if there's no potential difference, then the electrons have no reason to move. There is nothing compelling them to move. There is nothing forcing them to move. Where the water in this example is analogous to electrons, okay? In this case, when there is a difference in height, a difference in electric potential, electrons want to move from high potential to low potential. But in this case, they can't because the dam is blocking them. Okay? Electrons want to move from high potential to low potential, but they need a path by which to do it. This is our general understanding of voltage, and we're going to see it applied in circuits in just a moment after we cover another important topic, and that is current, as units of coulombs per second. Now let's try and understand that unit in context. Coulombs per second is defining how many coulombs of charge are moving through a given point every second. How many electrons or charge carriers are moving through a given point every second. All right? So if we're continuing the water example, let me redraw my dam here. But instead of a dam being here, I allow a small hole right here in the dam. I create a hole in the dam. Now water has the capacity to flow from a high potential to a low potential, okay? And since the water can flow from a high potential to a low potential, it will do that. Current describes how much water is moving through this hole every second. So the making of a hole in the dam is analogous to us connecting 2 points with a conductor, right? Electrons need to flow through a conductor. Now, circuits will be drawn using specific symbols, and you'll see the symbols are very intuitive, but it's up to you to know what the symbols mean. No one's going to tell you what the symbols mean. All right, so I'm going to draw one out for you right now. Very simple circuit. You can see that it looks like a box, it looks like a loop, all right? And that is a defining characteristic of a closed circuit. A circuit is a loop. Charge must flow in a loop. It flows in a loop. Remember, conservation of charge was a topic we discussed in the previous unit video. Conservation of charge dictates that if charge moves from point A to point B, charge must also move from point B to point A. If you have an open circuit, meaning the loop is broken, you have a hole in the loop, means you have open circuit, therefore no current can flow, no electrons can move, period, okay? What does that mean? It means that even though there's a break in the circuit here, it means that charge movement from here to here is still forbidden. It is still prohibited. Why is that? Because if charge moves from here to here, charge must also move from here to here. Okay? If one of the pathways or any pathway is interrupted, charge cannot move anywhere in the circuit. So let's get back to what I was talking about, symbols. Okay? You see that I have two distinct symbols in this circuit. First and foremost, you notice that around these two symbols, there is a solid line connecting them. A solid line in any circuit represents a conductor or wire. This symbol, now it's very important to pay attention to the length of the lines here. This symbol with two parallel lines, one short, one long, is a battery. This is a battery, okay? The length of the lines is important because the long line is always your positive side of the battery, and your short line is always the negative side of the battery. If you turn to the front page of your AP Physics reference table, you'll notice that in the bottom right-hand corner there is a list of assumptions, okay? In that list of assumptions, it states that current is defined as the direction in which positive charges flow. So given that assumption, we would say that current flows from the positive terminal to the negative terminal. That is what that means, okay? Now, that might be a little confusing. Why is that? Because even though we are saying that current flows from positive to negative, positive charges are not moving, okay? Electrons are moving. So if positive current flows from positive to negative, it means that positive charge flows from positive to negative, but positive charge isn't moving. Negative charge is moving. Positive charge moving in one direction is the exact same thing as negative charge moving in the opposite direction. So even though we are saying that current flows from positive to negative, that means that electrons, negative charges, flow from negative to positive. Electrons are flowing in the opposite direction in order to give us this positive current. Another symbol, before I get into that, this battery is going to be the source of our voltage. It's going to be the source of our EMF. Often you see batteries labeled 1.5 volts, 3 volts, 5 volts, 9 volts, okay? You can put a 9-volt battery in the circuit. In that case, your EMF would be 9 volts. And that is the potential difference that you are supplying to the circuit, all right? A battery is pretty much you supplying a situation in which you have a high potential and a low potential. That is what a battery supplies. And the rest of the circuit is the tube through which water can flow from high potential to low potential. Think of it like that. The battery is the dam that holds all of the water at a potential difference, and the circuit is the tube that allows the water to flow from high to low. Okay. This right here, what does this symbol mean? This is a resistor. A resistor, as the name implies, resists the flow of current. It resists the flow of electrons. And how does it do that? It's useful to understand how it works on a molecular level, okay? A resistor, pretty much what it is, it's a really, 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 really thin pipe. If you guys understand how water moves, which you should because fluid dynamics is a unit, if you try and shove water through a really big, really wide pipe, the water can move very easily. The water can move very freely. But if you take a huge dam and with a potential difference like this, and you allow water from high potential to move to low potential through like a straw, that's a really, 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 really thin pipe. So that pipe resists the flow of water from the high potential to the low potential, okay? And if you make the pipe thinner, you increase the resistance. If you make the pipe thinner, the flow of electrons is resisted further. If you make it bigger, you have less resistance. So that is what a resistor is pretty much in a circuit. It's a really, 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 really thin piece of wire. Really thick wire has really low resistance. Really, really thin wire has very high resistance, okay? So resistance is a unit that we define with the capital Greek letter omega. And the unit is ohms, spelled like such. And that is what a resistor is. That finally brings us to the central defining equation of circuits, which is Ohm's law. And that states that delta V equals IR. Okay, what is delta V? Delta V has a specific connotation, and it means a voltage drop or voltage difference. Voltage drop or voltage difference is measured across a component, or is measured across a series of components. So that requires us to enter into a new conversation about how voltage is measured. Okay? So let me clear up some of this gunk surrounding my circuit so I can better explain how we treat voltage drop, okay? Voltage drop is a voltage drop across a component, like I said, okay? So let's continue with the example that this is a 9-volt battery. So a 9-volt battery means that the voltage drop, the delta V across the battery, is 9 volts. So therefore we can say that at the negative terminal of the battery we measure 0 volts, and at the positive terminal of the battery we measure 9 volts. Means as you go from one side of the battery to the other, you go from 9 volts to 0 volts. Okay. Another thing is that voltage numbers, your voltage measurement, can only ever change across a component. Okay? What that means is that voltage through any wire is constant. It's the same everywhere. Which means if I measured the voltage right here, my voltage would be 9 volts, and if I measured my voltage right here, my voltage would be 9 volts. Okay? The voltage is constant throughout any conductor. Voltage only changes across a component. Like I just said, 0 volts would be measured at this point, 0 volts would be measured at this point. Therefore, the voltage drop, the delta V across this resistor, is the voltage before the resistor minus the voltage after the resistor. So the voltage drop across the resistor is the full 9 volts. That stands in contrast to a different circuit where if I had another 9-volt battery and I were to draw it as such with 2 resistors in it, like this, I would measure 0 volts right here, I'd measure 9 volts right here, and assuming that both of the resistors are the exact same resistance, I would measure 4.5 volts right here. Voltage drop across this resistor is 4.5 volts. And the voltage drop across this resistor, delta V, equals 4.5 volts. Okay? But if I consider both resistors at the same time, I can say that the voltage drop across both resistors is 9 volts. Hope we understand how that's measured. So this equation can therefore be interpreted as the voltage drop across a component is equal to the current through that component multiplied by its resistance, or the voltage drop across a series of components equals the current through those components multiplied by their total resistance, or the voltage drop across a whole circuit equals the current flowing through the whole circuit multiplied by the resistance flowing through the whole circuit. Now this equation, delta V equals IR, is expressed on your reference table as it's I equals delta V over R. Again, you can see that they're the same equation. It's just one manipulation. Another equation that you have on your reference table is the equation for power, such that capital V equals delta V times I, equals voltage times current. Like we covered in AP Physics 1, the units for power are joules per second. As we covered just now, the units for voltage are joules per coulomb. The units for current are coulombs per second. We can see why our units agree. Power is very, very simple topic in this class. It's usually almost always just asked as a side part of an FRQ maybe, where you would just be given or have already calculated potential and current, and you'd just be asked, what's the power dissipated by this? Okay, so back here now that we're on the topic of resistance, we need to, of course, introduce the calculus concepts that might exist beyond the algebra. So we discussed that resistance is equal to the resistivity of a medium multiplied by the length divided by the cross-sectional area. But you may often find materials that have a resistivity that changes with respect to length, with respect to what place you are on the conductor, on the wire. So in the case where you have a rho, you have a resistivity that is a function of length, then your differential resistance contribution would be equal to the value of your resistivity function multiplied by the length differential divided by area, okay? Because since the resistivity changes at a continuous rate, then we can only evaluate the resistance contribution from differential lengths, and therefore we need to integrate both sides in order to get the resistance of our whole conductor as an integral here with respect to length and our resistivity function. Not as complicated here. There's no change of variables. Your differential and your function are going to be given in the same variable. Moving on from there, series and parallel circuits. Let me draw a circuit for you like this, where I have my 9-volt battery, where I have one resistor here, and I have one resistor here. Let me ask you all a question. What voltage do I measure right here? 9 volts. What voltage do I measure just before the resistor? 9 volts. What voltage do I measure right here? 9 volts. Why is that? Isn't there a component between them? No. There is no component between these two places. These places are connected by a wire. And by definition, all points connected by a conductor are at the same voltage. Same thing applies here. All points connected by a wire are at the same voltage. You have 0 volts here. Therefore, what's the voltage drop across this resistor? 9 volts. Same as the voltage drop across this resistor, 9 volts. So this is an example of a parallel circuit. Okay, what do we mean by parallel? It means that the loads, in this case the resistors, are each included in their own loop. Okay? That means that if I break this loop, if I cause an open circuit right here, current is still going to be able to flow through the second load, through the second resistor, and complete the circuit. Okay? A parallel circuit means I can break one of the parallel circuits and current can still flow through the other. Here you would say that the two resistors are arranged in parallel. Consequently, this is an example of a circuit in which the two resistors, the two loads, are arranged in series, wherein if I break the circuit right here, current can't flow anywhere in the circuit. There is no complete loop that current is able to make. And you also notice the difference in potential difference. In this case, there's a 9-volt potential difference across both resistors. In this case, the voltage difference is divided across each resistor. Now, when analyzing circuits, we are going to reference Kirchhoff's laws, okay? They're often referred to as Kirchhoff's rules, whatever you want to call them, I don't care, okay? Number 1 states that all current entering a junction must be equal to all current leaving a junction. Okay? What do we mean by a junction? A junction is pretty much any point on the circuit. It's a derivation of conservation of charge. All the charge that comes into a point must leave the point. If we consider this as our point, all the current that comes in on this wire must leave through that wire. If we consider this a point, all the current that comes in from the right and from the top must leave through the left. The second rule is that the voltage drop across a complete loop is equal to the IMF. The voltage drop from one end of the loop to the other must be my 9 volts, okay? That's because in my battery, one end of the battery is plus 9 volts, the other end of the battery is 0. Meaning that by the time the current reaches the negative terminal of the battery, its electric potential must be entirely dropped from 9 to 0. Let's do some practice with Ohm's law, okay? Let's consider the 2 series and parallel examples I just gave you, okay? Let me clean this up a bit so I can give us some numbers to work with, okay? So first and foremost, we're going to work with the 5-volt battery to make it easier. Means in this example, I'm going to have the 5-volt battery. In this example, I'm going to have the 5-volt battery. Okay? Now, my first question to you is going to be, in which direction does current flow? Current flows this way around the battery, like this. Now, if I were to reverse the polarity of the battery, meaning I had the long side on the bottom and the short side on top, now which way does current flow? Now it flows this way around the battery. The resistance of my bottom resistor is 1,000 ohms. The resistance of my top resistor is 500 ohms. Find the current flowing through the circuit. So first we need to discuss what exactly do you mean when you say current flowing through the circuit. Current through the circuit means current flowing through the battery. Current can only change at a junction in which 3 or more wires meet, okay? Now that stands in contrast to voltage, which can only change at a component. So the current flowing through the wire here is going to be the same as the current flowing through the wire here, okay? Because they are both connected through the current flowing through the wire here will be the same as the current flowing through the wire in the middle of the resistor, okay? Because current doesn't change at a component, current changes at a junction which has 3 or more participants. So current would change here, okay? This junction has only 2 participants, so current here would remain constant. So current changes once at this junction, once at that junction. In the series circuit, there is no junction at which there's no junction at which 3 or more wires converge. Therefore, the current in the circuit, the current through the battery, is the same everywhere, okay? Which is in contrast to this example, which does have junctions in which 3 or more wires meet, so the current is not the same everywhere. Let's go back to this example. Granted that the current is the same everywhere, I need to calculate the current in one component, or in one spot, and then I will know the current everywhere, the current through the circuit. We need to understand how to determine our potential difference, okay? If we wanted to consider one of the components individually, then we would need the potential difference across that component, okay? But I don't know the potential difference here in the middle. I don't know that potential difference, so I can't consider one of the components individually, right? I only know the potential difference across both of them. So I would need to consider the potential difference across both components, right? But how do I consider 2 resistors at the same time? Well, we have equations for that. We have equations for series resistance, and we have equations for parallel resistance. On your equation sheet, you will know that the net resistance of resistors in series is the sum of all the resistors in series, where the equation on your reference table states that the equivalent resistance of parallel resistors is equal to 1 over the resistors added as such, okay? Which can also be rewritten as 1 over the net resistance equals 1 over Ri plus 1 over R double I, etc., etc. Given that this equation on our reference table says that the net resistance of a set of resistors in series is equal to the sum of their individual resistances, I can say that in this example, if I bring it over here, I can say that the net resistance in my series circuit right here is 1500 ohms. So the net resistance across both resistors is 1500 ohms. I know that my potential difference across both resistors is 5 volts, because I've got 5 up here and 0 down there. Therefore, by this law, by Ohm's law, 5 volts over 1500 ohms is going to give me, bring out the calculator, 5 divided by 1500 gives me that my resistance is 0.003 amps. That is the unit for current. Amperes, also often abbreviated as amp. So let's do the same example here. I'm dealing with a 5-volt battery, where this is a 500 ohm resistor, this is a 1000 ohm resistor. So let me calculate the equivalent resistance of the resistors in parallel, okay? So 1 over the net resistance equals 1 over the first one plus the second one plus the third one, so on and so forth. So 1 over 500 plus 1 over 1000 equals, well, 3 over 1000, 0.003. So that's this side of my equation. Now the left side equals 1 over the net resistance. Therefore, my net resistance in the parallel example is 1 over 0.003, 333.3 repeating ohms. So if you notice here that the net resistance of both my resistors is 333 ohms, which is less than the resistance of either resistor. How does that happen? Let's understand that in context. If I have a dam and I have a super thin straw, there will be a great opposition to the flow of water through that straw, connecting the two sides of the dam, okay? But if I add a second super thin straw, now there is less resistance to the flow of water, because the water now has more room to move. It has one straw and a second straw. Therefore, the net area through which water can move has increased. So our resistance to the flow of water has decreased. That's why our net resistance in the parallel example is smaller, because we are connecting two resistors, two straws to the dam at the same point. Whereas here, you would be connecting one straw to the end of a second straw. And in that example, you would just be increasing the length of the resistor. Whereas here, you would be increasing the net area of the resistor. And we discussed how area is inversely proportional to resistance. Anyway, let's get back to calculating the current through our circuit, or the current through the battery. Our potential difference across the circuit, delta V equals 5 volts. Delta V divided by R, 333.3 repeating, equals our current through the circuit. Okay, 5 divided by that gives us our current as 0.015 amperes. So notice how our current through the parallel circuit is greater than our current through the series circuit. So before we move forward into another heavy topic, we need to cover one logistical thing, which is how we interpret meters. Okay? What do we mean by meters? We mean the instruments by which we measure voltage and current. Okay? So if I were to draw for you a circuit right here, or redraw the same parallel circuit I had earlier. Okay? If I had a voltmeter right here, which on your AP exam would be depicted as such, that voltmeter, where is it connected? It's connected here and here, which means this voltmeter is reading what? It is reading the potential difference from this point to this point. And so if this is a 5-volt battery, we see that the line connects these 2 points to the battery, therefore our potential difference should read 5 volts. How does the voltmeter alter the circuit? So first of all, we're only going to consider the case of the ideal voltmeter, wherein an ideal voltmeter allows 0 current to flow through. Therefore, an ideal voltmeter behaves like an open circuit. Meaning, if I connected a battery series with a voltmeter, no current would flow. I'd have an open circuit. I do not need current to measure voltage. I do not need water to be flowing across the dam in order for me to measure the water levels on each side of the dam. And the voltmeter does not allow current to flow so as not to impede other parts of the circuit. If the voltmeter allowed current to flow through it, then it would be taking away from current flowing through these resistors, and that would be altering our circuit in a way we don't want it to. A amp meter, on the other hand, would be depicted to you as such, and it would connect to your circuit like this. Okay? Now the amp meter allows infinite current to flow through. That doesn't mean infinite current flows through the ammeter. It means that the ammeter allows any amount of current to flow through it. That means that the ammeter has precisely 0 resistance. Okay, that is of course the case of the ideal ammeter. Okay, which means the ammeter here behaves just like a conductor with respect to the rest of the circuit, but it would allow us to measure the current flowing through this wire. It would allow us to measure that current. Okay? So pay attention to where these meters are placed in the circuit. The amp meter is placed where a wire should go because the amp meter, in the eyes of the rest of the circuit, behaves just like a wire. It behaves like a wire with 0 resistance. The voltmeter, on the other hand, behaves like an open circuit. So it would be placed parallel with a component. Parallel with something, okay? Because if you place a voltmeter series with anything, that means that no current is flowing through the component or collection of components that you have placed it series with. All right, moving on from there, we have the capacitor. Capacitor is a new type of component, okay? Now, as we go through the unit on capacitors, if you at all have trouble with this unit, don't take Physics C E&M. It becomes much more nightmarish in that class. Anyway, of course, if you have trouble with capacitors, come ask me, come join the Discord, ask me questions. What is a capacitor? A capacitor is a device that stores electric charge, okay? And I'm sure all of you are sitting there saying, if it stores electric charge, isn't that just a battery? No. And the difference is that a capacitor stores electric charge in the form of electrical potential energy. A battery stores electric charge in the form of chemical Gibbs free energy. You don't need to know what that means because you're not studying AP chemistry. A capacitor stores electrical charge as electric potential energy. Electric potential energy, again, being a topic we covered in the previous unit about electrostatics. If you need a simple refresher, If I have a positive particle right here, and I have a positive particle right here, and I keep them at rest, I hold them in place, these two particles have potential energy because these two particles repel each other. If I release them from rest, the particles will accelerate away from each other, using up electrical potential energy to gain kinetic energy. Same is true for a positive and a negative particle. If I hold them at rest, they have electric potential energy because once I release them from rest, they will accelerate towards each other and convert their electric potential energy to kinetic energy. The parallel plate capacitor is the reason why the symbol for the capacitor is as follows. It is two plates of exactly the same size, parallel lines. That's a capacitor, that's a battery. Battery different size, capacitor same size. Okay? Now let's consider a capacitor enlarged, okay? Where you have one end of the circuit connecting to one plate, the other end of the circuit connecting to another plate. And that's pretty much the setup for a parallel plate capacitor, where if I turned this around and I looked at one of the plates would look like a square. It would be like, this is one of my plates and my circuit is connected to the back. If I were to connect this parallel plate capacitor to a battery, that battery, again, long side being positive, short side being negative, positive charges would flow this way and positive charge would accumulate on this plate. Negative charge would flow this way, negative charge would accumulate on this plate, okay? And now charge will accumulate on that plate for a time until so much charge has accumulated on that plate where the plate now has a potential difference delta V. And the battery will continue to add charge to the capacitor, will continue to charge the capacitor until the voltage, the potential difference across the capacitor equals the potential difference across the battery, right? The battery will continue to fill up the right side of the reservoir until they are at the same height. Pretty simple to understand. The current stops flowing, the capacitor stops charging when voltage difference is the same, okay? Now from there, let's take a look at some of the equations we have on our reference table to define capacitors, okay? First of which, you will see this equation, capital C equals kappa epsilon A over D. Kappa being our Greek letter that looks like a K, epsilon naught being the vacuum permittivity that we covered in the previous unit, area being the area of one of our parallel plates, distance being the distance by which they are separated. The capacitance, what is capacitance? Capacitance is the amount of charge that our capacitor can store at a given potential difference, okay? Which brings us to our second equation, that our capacitance C is equal to our charge on the capacitor Q divided by the potential difference across the capacitor. Now, the equation is given to you on your reference table as such, but you can see that they are the same equation, which means this equation tells us that given a constant capacitance, as we raise the potential difference supplied by the battery, a greater amount of charge will collect on the capacitor, okay? Now, the capacitance of a capacitor is a constant. It is a definitive characteristic of the component, definitive characteristic of the capacitor, all right? And how do we define the capacitance of a capacitor? It's equal to the area of the parallel plates divided by the distance between them, multiplied by epsilon naught, multiplied by the dielectric constant K. We're going to cover exactly what dielectrics are in just a moment. Given that charge is accumulating on these plates and charge is never allowed to flow between the plates, this is an open circuit. And it behaves exactly like an open circuit once the plates become charged, because once the plates become charged, the potential difference is the same, no current is allowed to flow, which is exactly the same result as having an open circuit. However, when the plates are completely discharged, there is no charge on the plates, current is allowed to flow freely as if there were zero resistance, okay? Which says that if at the instant the circuit is closed to a discharged capacitor, current flows as if there is no resistance, which means you have approximately infinite current. However, after a long time has passed, after the capacitor has become fully charged, the circuit behaves as if open circuit and zero current is allowed to flow, okay? The test usually states after a long time has passed, but in reality, capacitors charge in usually a few or microseconds. I meant to say microseconds. So what is a dielectric? A dielectric is a non-conductive material inserted between the parallel plates of a capacitor. That non-conductive material is called your dielectric, okay? What happens inside a dielectric is, as, let's say, negative charge accumulates on the negative plate, that negative charge repels electrons in the dielectric. So the negatively charged plate will repel electrons in the dielectric and leave the negatively charged plate adjacent to the positively charged side of the dielectric, which is a process we covered in the previous video. Now that we have induced a dipole in the dielectric, positive charge on the right, negative charge on the left, positive charges attract the negative charges, which means this positive charge on the dielectric allows more negative charges from the battery to flow onto the plate, okay? Because positive attracts negative. In the same sense, it allows more positive charges to flow from the battery to the positive plate because the negative electrons in the dielectric are attracting them. Or, if it would be more precise, the negative electrons in the dielectric are repelling electrons from the positive plate. Okay? Therefore, a higher dielectric constant defines a dielectric that has a greater ability to polarize as such. And a greater ability to polarize as such will allow more current, to flow, and will allow more charge to accumulate on the plates. Okay? So an increase in the dielectric constant increases your capacitance. Okay? The remaining equations you have on your reference table to define capacitors are to define capacitors in series and parallel. Those equations are the exact same equations as the series and parallel equations for resistors, however flipped. For resistors, the net resistance for a series of, for resistors in series is just the sum of the resistances. However, the net capacitance for capacitors in series is the 1 over thing that we covered earlier. The equation for capacitors in parallel is the sum of the individual capacitances. Okay? So the operation of series and parallel capacitors is exactly the same as the circuit concepts we've been covering. And again, the associations for series and parallel capacitors are just flip-flopped with the equations for series and parallel resistors. So right next to Ohm's law being V equals IR, there are two other equations that are very, very important to our understanding of circuits. And those two equations are Kirchhoff's laws. I'm probably butchering that name and I don't know how to spell it, but we are physicists. We don't memorize names and dates. So Kirchhoff's laws. Number 1 is that the sum of all potential differences in a circuit must sum to 0. Okay? Let's exhibit what that means. If I have a circuit where I have a battery here connected to like a capacitor and then a resistor, and then that resistor is set up in parallel with 2 more resistors. Okay, so like not the easiest circuit. However, at every component in the circuit, there is some voltage drop associated with that component. There's a voltage drop across the capacitor, voltage drop across the resistor, and voltage drop across the set of resistors. But there is also a potential difference across the battery. Okay, so if the potential difference across the battery is 5 volts, then let's say I would have a 2 volt potential drop across the capacitor, 1 volt potential drop across this resistor, and a 2 volt potential drop across this collection of resistors. Okay? This law states that this is a drop in 2 volts, this is a drop in 1 volt, this is a drop in 2 volts, and this is a gain. It states that the voltage drops across the entirety of the circuit must equal the voltage gain of the battery. That's what it means. Okay? Second law is the junction law. It means that all the current flowing into a junction must equal all the current flowing out of a junction. Okay, this is an example of a junction. All the current flowing in must either go to the left or to the right. This is an example of a junction. All the current flowing in must flow out. Conservation of electric charge. Current in must equal current out. Using those laws, we are going to introduce the concept of the capacitor in what's called an RC circuit. An RC circuit is simply defined as a circuit that contains both capacitors and resistors. Let me draw a simpler circuit where I have a 5 volt battery with a resistor series with a capacitor. Okay? Again, long side is the positive end, short side is the negative end. And we used Ohm's law to understand stuff like the resistance of the capacitor, the current flowing through the circuit. But capacitors behave very differently. Okay? So as we discussed previously, when the switch is initially closed, we have a capacitor that behaves like it is just a wire, just a closed circuit. But as time goes on and a long time has passed, enough charge has accumulated on the capacitor such that the potential drop across the capacitor equals the potential gain across the battery and no current flows. Okay? So the understanding of current flow through the circuit starts at very high current flow and ends at 0. So therefore our current flow through the circuit, our charge on our capacitor, our potential difference across our capacitor will be functions of time. Okay? So that is going to be the derivation we are going to try and get at here. Okay? We are going to try and find an equation that models the charge that accumulates on this capacitor as a function of time. Now, this is not some fun exercise. This is often an FRQ that shows up on the AP Physics C E&M exam, deriving this equation that I'm about to show you. Okay? So pay attention. The beginning of this derivation starts with Kirchhoff's loop rule. Okay? It says that the sum of voltage drops in the circuit equals 0. Another way of writing that is the EMF supplied by the battery must equal all the voltage drops, negative values across the circuit. Okay, so in the case of an RC circuit, there are two sources of voltage drop. You have voltage drop across the resistor, which is IR, and you have voltage drop across a capacitor. Let's go to our reference table to find the equation for that. We are shown that C equals Q over delta V, stating that the voltage drop across the capacitor is the charge on the capacitor divided by the capacitance, plus Q over C. So this is our Kirchhoff's loop rule starting equation. Simply states that the voltage gained across the battery, 5 volts, in this particular case, must equal the voltage drop across the resistor and the voltage drop across the capacitor. So we are trying to find a function, charge as a function of time. So I see charge present in my equation. However, I need a differential to associate it with. How convenient. We discussed that current is the derivative of charge with respect to time. So this can be rewritten as epsilon equals dq by dt r. Now that we have a differential equation, we need to separate variables. So I'm going to save you all of the algebra. dq by dt equals epsilon minus q over c, all divided by r. I'm sorry if my q's look like a's. I have bad handwriting. Anyway, now we have our differential equation isolated in the form we want. So the next step in solving the differential equation is our separation of variables. Let me get this circuit out of the way so it's not clogging up my valuable whiteboard space. Okay, so dq over epsilon minus q over c equals dt over r. Okay? Next, what I can notice here is I can manipulate this to get my capacitance on the right side. And you'll see why that's important in just a moment. I can multiply both sides by 1 over the capacitance. So 1 over c times dq over epsilon minus q over c equals dt over rc. And I'm going to bring this over here. That's going to say dq over epsilon c minus q equals dt over rc. The reason RC is significant is because I believe this equation is given to you on your reference table. Yes, your time constant, the Greek t, equals RC. So why is that important? So the time constant is a metric that indicates the rate of growth or rate of decay of the charge on the capacitor. Okay, so a very low time constant is going to mean that it charges very fast. A very high constant means it charges very slowly. Okay? So I'm going to wipe away RC here and replace it with my time constant. So now I'm free to integrate both sides. And I'm going to integrate the left side from zero charge on my capacitor up to some final charge Q that I want to know. And I'm going to integrate the right side of my equation from 0 time to after some time t has passed. Okay? So let's find our antiderivatives. The antiderivative left side is going to be the negative natural log of our epsilon c minus q equals our t over time constant. Evaluated, of course, 0 to t, evaluated 0 to q. Okay? So we need to take a moment and remember what our variable was here. What am I plugging in? I'm plugging into q on the left and I'm plugging into t on the right. Not time constant, t. Now, dealing with negative natural logs when I'm evaluating bounds here is kind of annoying. So what I'm going to do is I'm just going to take this negative and I'm going to move it over to my right side to make life easier. Okay? So now let's evaluate the left side of our equation at our bounds. We've got the natural log of epsilon c minus capital Q, because we're evaluating at capital Q first, minus, evaluated at our bottom bound, natural log of the EMF times the capacitance minus 0, means we have nothing left there. Okay? Using log rules that you should have learned in pre-calc, we're going to rewrite the natural logarithm as epsilon c minus capital Q over epsilon c equals the right side of my equation, which is just going to simplify to negative t over the time constant. So now that I'm here, I've finished all of my integration, I've done my evaluating at my bounds. I was trying to find charge on the capacitor as a function of time, so I need to isolate Q. First of all, we're going to raise e to the power of both sides. It's going to give us the electromotive force times the capacitance minus charge Q over the electromotive force times the capacitance equals e to the negative t over time constant. I'm going to multiply both sides by EC right here. I think I'm losing my voice. I'm sorry if it sounds like that. And so now I'm going to subtract EC from both sides, so I have negative Q equals EC. I keep saying E, I mean epsilon, to the E to the T divided by time constant minus my EC here. And now I just need to multiply both sides by -1 to get my charge Q equals epsilon C minus epsilon C times E to the -T over time constant. And this I can write in a much neater form as Q equals epsilon C times 1 minus E to the T over time constant. That, therefore, is my Q as a function of time, right there. And time is present right above my E. So if I were to graph this to demonstrate how it looks, if I have time on my x-axis, charge on the capacitor on my y, the charge on the capacitor would grow like this and then asymptote towards a maximum value that can be stored on the capacitor, which would be given by your equation right here. Okay? But I said a lot of things before. I said I wanted to know charge, I wanted to know potential difference, I wanted to know current. But what's important to know now is, now that I have charge as a function of time, I can get my others with that, okay? Let's say I wanted to find potential difference across the capacitor as a function of time. Well, we know that potential difference across the capacitor is just our function Q divided by C, right? So if I rewrite this here, Q equals C times the potential difference. So I need to divide both sides by C to get potential difference by itself. So therefore, potential difference across the capacitor as a function of time equals epsilon times 1 minus E to the time constant over, or T over time constant, I should say. Right there. We also know by Ohm's law that V equals IR, okay? And in a series circuit like this, the current flowing through any part of the circuit is equal to the current flowing at all parts in the circuit. So, if I want to find the current flowing through my circuit, that is the potential drop divided by resistance. So, if I wanted to find current through my circuit as a function of time, it would be epsilon over resistance times 1 minus E to the T over time constant. Now, one thing of note, whenever you see the letter R, whenever you see the representation of resistance in this derivation, it doesn't mean the resistance of the resistor right next to the capacitor. The resistance, it refers to the total resistance in the circuit. So if I had a circuit like this and I was trying to do my derivation for capacitor, I would need to calculate the equivalent resistance of the whole circuit, okay? If you forgot what that means, it means if I were to treat this whole mess as if it were one resistor, what would be the resistance of that resistor? And we know how to calculate that from our series and parallel resistance equations. All right, thanks guys.